Okay, so the question is, the ENLIL spiral shows a curved line between every object and the sun, referred to as the IMF line. I assume it has something to do with magnetic connection. Could you please elucidate on the nature of that connection? Gladly, I'll gladly do that, Atmanhotep. So, what we're talking about here is this thing. By the way, there was an X-flare just a couple of hours ago. But then we'll tell you about it, no doubt. So, okay, here you can't actually see any lines, so we have to go someplace else like this ISWA. Here on heliosphere you can see the ENLIL spiral, in case you want to reproduce what I'm about to show you. So, yeah. So these lines that you can see here are exactly that. It's the connection of Earth, in this case, this yellow thing, to the surface of the sun. And what kind of connection is this? Well, it's a magnetic connection, just as you've said. So it's quite literally the magnetic field lines exiting the sun and getting to Earth. So it's the interplanetary magnetic field, right? It's the solar wind magnetic field, you might call it as well. And well, if you remember one of the previous episodes where I talked about like how particle interacts with magnetosphere of Earth, this doesn't really reach Earth. That's kind of what I'm about to say. Like it reaches vicinity of Earth, right? But we have our own magnetosphere, which kind of interrupts this flow, if you wish. So it's not like like the ground is connected to the sun or something. No, no, no. Like you have to include all the dynamics of plasma in our magnetosphere into consideration as well, obviously. But if you are somewhere near Earth, it would connect to you, yes. Or, for that matter, if you're anywhere else, you would connect to some point on the solar surface. In fact, there is, sorry about this, there is this service also has a map which shows where exactly we're connected to, and it's here. You can see Earth, which is incredibly weird, to be honest. I don't know why it's here. In fact, I doubt it is here, because this is from SDO, basically from geostationary orbit. So this is how we see the sun. I have no idea why the connection point is here. It should be usually somewhere around here. It's like to the right from the center, because again, the solar wind is curved, right, into this Parker spiral, because the sun spins, I mean, around its axis, and that it curves the solar wind and the magnetic field lines associated with the solar wind. So you would expect, you can see that this line emanates from somewhere to the right, like this is a top-down view. So if we're looking at the sun, it should be slightly to the right. So you would expect it to be somewhere here. I don't know why it is here. Maybe it's some sort of glitch. No idea, honestly. But yeah. So what kind of connection is this? Again, I'll remind you that you can see the polarity. IMF is interplanetary magnetic field, basically the magnetic field of the solar wind. So what is negative polarity? It means that the magnetic field line enters the sun. So it's this blue area which projects into infinity sort of here. Not to infinity really, but around, what is it, 2 AU, right? 2 astronomical units is what we're seeing here. It's actually curved significantly, like somewhere around between Jupiter and Saturn. Actually, this curvature becomes so high that it wraps a whole 360 degrees, okay? So at infinity it would be very complex. But anyway, so yeah, this is what's happening. The blue lines means the blue thing, the negative polarity, south polarity, means that the lines enter the sun, and the red one, the north, means that the lines exit the sun. Okay, so this is what's happening. And what kind of connection is this? What does it mean that we're connected to this area on the sun or that area on the sun? Well, it means that particles, charged particles, they move. How do they move? They spiral around magnetic field lines, right? Just like indicated here. So imagine this magnetic field line connecting us to the sun. It would mean that all the particles that are situated here can travel along this line, spiraling around it. Okay, that's why when let's say there is a solar flare in a region which we are connected to or somewhere nearby, we can see a proton event, like something here, spikes, because the fast particles which are produced by the flare just jump on this highway, so to speak, on this line of connectivity, and they arrive at Earth really quickly. Like these fast particles, they have a they are fast, so they have a velocity of a significant fraction of the speed of light, could be like 30 to 40%, maybe even higher. So they arrive in like maybe 20 minutes, whereas the regular plasma, the CME, takes like a couple of days to reach us. So it's a big difference, right? So to answer your question shortly, it's just a line of the magnetic field, okay? And yes, it connects us to the sun, in the sense that we may receive, let's put it this way, it's much easier for us to receive any sort of charged particles from the region connected to us than any other region, really. Because again, the conductivity of solar wind is orders of magnitude higher along the lines of force, along the magnetic field lines, rather than in perpendicular direction. There's basically no current in perpendicular direction. And speaking of current, by the way, in the area where we have a transition from north to south magnetic field, we have the current sheet, right? This is the white one, the white thingy. That's where the current flows. Why is the current? You can see it's like a cross section from the vertical cross section, sort of. We're seeing the Earth kind of from the side here, so you can see it's very twisted, the current sheet. So here is the region of south polarity, where the lines enter the sun, and here's the north polarity, where the lines exit the sun. So we're currently connected to the north. So the lines of force go to us from the sun, whereas here they go into the sun from us, okay? So why do we have a current between those two different regions? Well, it's because, again, if you have different magnetization here and here, there should be a current according to Maxwell's equations. There should be a current that causes this change. And that's how the current sheet appears. And generally speaking, in plasma, if you have two regions of different magnetization, you will always have a current sheet between them. And some examples we've already examined, what was it, 2 weeks ago, when I talked about how particles move in the magnetic field of Earth. Okay, hopefully this answers your question. Yeah.